At 4:38 in the morning on March 7, 1951, Norfolk and Western Y-6B number 2185 coupled onto a string of 120 loaded hopper cars at the Dry Fork Branch interchange in Iager, West Virginia, and began the long pull east. The consist weighed 14,500 tons. The locomotive weighed 291 tons. Its boiler held water at 300 pounds per square inch. Its tractive effort, the force it could apply to the rail, was rated at 166,000 pounds. Nothing built in North America before or since produced more pulling force from a single steam engine at slow speed. The coal in those hoppers had come from mines scattered across McDowell County's Pocahontas Seam, one of the thickest and highest BTU bituminous coal deposits on the planet, where it had been loaded at timber-framed tipples where the raw seam was crushed, screened, and weighed before dropping through chutes directly into waiting open-top hopper cars. Each car held between 50 and 100 tons. Each car had been positioned at the tipple by a mine locomotive, spotted precisely under the loading chute, filled, and moved out to the assembly siding where the road locomotive would find it. From Iager to Lambert's Point in Norfolk was 340 miles. The grades between them, the Alleghenies, the Blue Ridge, the ridges of the Great Flat Top, were among the steepest sustained mainline grades in American railroading. The Y-6B didn't accelerate. It held the rail and pulled. The coal railroads of Appalachia were not general freight railroads that happened to carry coal, and they were coal railroads that happened to carry everything else. Before we go further, if this kind of story matters to you, consider subscribing to the channel. Every video here is built around the systems that actually hold this country together. The power lines, the rail corridors, the infrastructure that most people never think about until it stops working. If that's the kind of documentation you want to keep watching, the subscribe button is how you tell us. And we want to hear from you. Did you work on a transmission line, a railway, a pipeline, a hydroelectric facility? Did a parent or grandparent spend their career maintaining infrastructure like this? Keeping the lights on, keeping the freight moving? Leave it in the comments. These stories belong in this record. Now, back to the system. The fundamental problem of Appalachian coal railroading was geological. The coal was in the mountains. The ports and steel mills were on the coast and in the valleys. The only way from one to the other was over or through some of the most difficult terrain in the eastern United States. The railroad had to climb to reach the coal and descend to deliver it. And in both directions, the physics of a heavy train on a steep grade were the dominant engineering constraint. The Norfolk and Western's main line east of Roanoke climbed the Blue Ridge at grades reaching 1.5% before descending toward the tidewater terminals. West of Roanoke, the Radford Division's eastbound Allegheny climb required helper locomotives at grades that the Y-6B could not conquer unassisted. On the Chesapeake and Ohio's Allegheny subdivision through the New River Gorge in West Virginia was one of the most photographed railroad corridors in America. Its steep walls and S-curves requiring precise train handling to keep loaded consists under control on the descent. The Baltimore and Ohio faced the same terrain at a different angle. The historic main stem from Baltimore to Wheeling, West Virginia, crossed the Allegheny front at the Sand Patch and Cranberry grades. Sections where westbound empty trains climbed against the grade, and eastbound loaded trains had to be carefully braked to prevent runaways. Helper locomotives, pushers, were stationed at the foot of each major grade. When a loaded drag arrived, a helper coupled to the rear and pushed while the road locomotive pulled. On the steepest sections, about 3 or 4 locomotives might be working a single train simultaneously, all of them burning coal from the same mountains they were crossing. The open-top hopper car was one of the most specialized pieces of railroad equipment ever mass-produced in the United States. Every element of its design was dictated by coal. The car was open on top to allow loading from above, from the tipple chute or the mechanical loading facility. The floor angled inward to a series of drop doors at the bottom, allowing the car to discharge its load by gravity when the doors were opened over a track-level hopper or receiving bin. The side walls were sloped to prevent coal from sticking in corners. The car was built low to keep the center of gravity down on curves and grades, and its wheelbase and truck design were calibrated for heavy unit train service. And the Norfolk and Western built many of its own hopper cars at its Roanoke shops. At its operational peak, the N&W rostered more than 25,000 freight cars, the overwhelming majority of them coal hoppers. A standard post-war N&W hopper held approximately 50 to 70 tons of coal. By the mid-1950s, newer 100-ton cars were entering service. Depleted fields account for 78% of total underground natural gas storage capacity in the United States. More than 3,000 billion cubic feet, held in hundreds of fields distributed across the producing and consuming regions of the country. The weight of a fully loaded hopper car determined nearly every other operational parameter. Locomotive tractive effort requirements, coupler strength specifications, bridge weight limits, track geometry standards. The coal car was not a passive container. It was a constraint around which the entire railroad was engineered. The N&W tracks reached Lambert's Point in Norfolk in 1886. Within 45 years, the port of Hampton Roads had become the largest coal shipping point in the world. Lambert's Point Pier 6, the primary N&W coal loading facility, in use since 1962 and still operating today, was built around the Rotary car dumper. A loaded hopper car was uncoupled from its train, rolled onto the dumper platform, clamped, and rotated 180 degrees. The coal fell by gravity into an underground receiving hopper. The car was returned upright, recoupled, and moved off. The process took about 90 seconds per car. From the receiving hopper, coal moved by conveyor belt to a surge bin, then to one of two 18-story ship loaders extending over the water. Twin dumpers working simultaneously could load coal at a rate of 8,000 tons per hour. In 1987, a record 123,000 tons were loaded in a single 24-hour period. The collier ships that carried it were bound for power plants and steel mills from New England to the Caribbean and across the Atlantic. The Baltimore and Ohio's coal terminal at Curtis Bay in Baltimore operated on the same logic as Hampton Roads, but with a different geographic catchment and a different coal character. At its peak, Curtis Bay processed approximately 15 million tons of coal per year. Its rotary car dumpers, eventually 3 independent units, could receive, dump, and return a loaded hopper car to the storage yard in under 2 minutes each. The terminal's triple dumper configuration allowed simultaneous operation without sequencing conflicts. The steel mills that received this coal through Baltimore and other ports were the downstream customers of the entire Appalachian coal railroad system. The blast furnaces whose coke demand drove the tonnages that moved the trains. The Norfolk and Western was the last major Class I railroad in the United States to abandon steam power. It completed its conversion to diesel in 1960. This was not an act of technological conservatism. It was an economic calculation. In 1952 and 1954, the N&W tested its Y6B class locomotives against electromotive division diesel sets. The results were close enough that the railroad was unconvinced. Steam won on raw tractive effort and fuel cost per ton mile, and diesel won on maintenance labor and operational flexibility. By 1958, The economics had tipped. The decision to fully dieselize was made, and new GP9 units from Electromotive and RS-11S from Alco arrived in numbers sufficient to retire the steam fleet. The last Y6B was retired in 1960. The coal trains kept running. The locomotives were different. The grades, the hopper cars, and the destinations were the same. The Appalachian coal railroad system was, at its peak, one of the most efficient heavy-haul industrial operations ever built. The N and W and C and O together moved approximately 60 million tons of coal per year at their wartime and post-war maximums. The B and O added another layer to the system, connecting the northern Appalachian coking fields to Baltimore and the Great Lakes, feeding the steel complex that built post-war American industry. What distinguished these railroads was not volume alone. It was the degree to which every component, human and mechanical, was specialized for a single purpose. The brakeman who could set retainer valves on a descending grade had a skill that existed nowhere outside this corridor. The mine locomotive engineer who could spot a hopper car to within inches of a loading chute did not learn that in a classroom. The pier operator who timed the dumper sequence to match the ship's shifting center of gravity was performing a calculation that had no manual. These systems were not automated. They were human. If this story gave you a clearer picture of what holds these systems together and what it takes when they come under pressure, subscribe to the channel when there are more corridors, more grids, more operations, and more decisions still to document. And if you have a connection to this kind of work, a relative who spent decades in a control room, a parent who worked a rail yard or a generating station, someone who was there when a system like this was tested, tell us in the comments. What did they operate? Where did they work? What do you remember them saying about the job? The most complete record of how these systems were built and run isn't in any report. It's in the people who were actually there.